Good morning, everybody, or afternoon, or evening, I guess, whenever you're watching. I'm making this in the morning. I just wanted to say, hey, hope everybody's doing well. Congratulations on finishing your work on trigonometry. We didn't get to go quite as in depth as we would have, obviously, if we were together, but hopefully that was a great overview and you're feeling good about that. Before we jump in with our next unit, which is all about circles, I want to just give you a quick rundown of kind of where we're headed. We have about 5 weeks left of the school year. So I'm going to give you just a brief overview just so you can kind of have a plan of where we're going. So the next 3 weeks, we're going to talk about circles. And this is a unit that can be a lot of fun if you understand it. And I'm going to try my best to do that and help you get there here with some videos and practice problems like we've been doing. After those 3 weeks, we are going to jump into a little bit of probability. And then with that last week of school, this will be summer. With that last week of school, depending on kind of what our instructions are from Mr. Berry and Mr. Young, we may do nothing. It's only a 3-day week for you, Monday, Tuesday, Wednesday. Or we might do some fun with transformations, which is usually a real quick unit. If we were together in person, it would be just more kind of fun activities, rotating, growing, shrinking, shapes, that kind of stuff. So I'm going to say transformations or none, because we're not quite sure what that's going to look like yet. As far as retakes go, moving forward, this week I will be offering a retake, I'm just going to say R for retake, of coordinate geometry. So you can check your scores on that and see if you're eligible for that retake. Next week, our retake will be over quadratics. After that quadratics retake, we're essentially done with retakes. We'll have done every retake that would be a grade that we assessed from winter break until spring break. So you can go back and retake anything that I've offered. You only get one opportunity at it, but if you have something that you didn't get to during that week, you can click on the previous weeks button on the website and go back. You can access anything that you'd like from our previous weeks as well. There is no timetable on that. It just needs to be to me by the end of the year. Once we're done with those retakes, in that 3rd week of circles, I'm going to post what I'm going to call kind of a would-be or a fake test. That's going to include circles and trig, and it will not be graded, and I will post the answer key. So no grade, answers posted. The idea there is I just want you to kind of see if we had been together in school, what that test would have looked like. There'll be some things about circles that we've worked on, some things about trig that we did. All I want you to do is use it as a chance to kind of practice and see, did I really understand this? Is there some stuff I might want to review before I move forward next year? Again, the answer key will be posted. You can check as you go. That's not graded. You don't have to submit it, and we'll talk more about that during that week. During these last 2 weeks, I think I'm going to post a practice final. Again, that will be kind of the same as the fake test of circles and trig. It will not be graded. The answers will be posted. It's just a chance for you to kind of see, hey, if we had been together here at the end of the year, what would the final exam have looked like? It'll be different than obviously what I would have given because I'll have to cut some things out that we didn't get to. But it'll be a good kind of recap of what we've done this year since winter break, and some things that I hope you have down and you understand. And again, no submission needed. You don't have to hand it in to me. You can check your own work. It's all just going to be kind of practice as we wrap up the year together. So hopefully that makes some sense. This will be kind of where we're headed here with our last 5 weeks of school, and then we'll be on summer break and hopefully back to kind of our normal routine next fall. But that being said, today we want to get rolling with our new unit, which is circles. And I want to reiterate before we get started the importance of those practice problems on the website. If you're just watching the videos, you're only getting about 30% of what you can get out of these weeks. Where the real learning comes is taking what I talk about in the videos and applying it to practice problems. So make sure that you're doing that. There will be 3 separate pages posted this week. Each one of those includes a different skill that we're going to talk about in this video. So make sure that you look at each one. Don't just do the first one and say, oh, well, I did my practice. Pick a couple problems from each page. Make sure that you get all of that practice in. All right, let's get started. So today we are introducing and talking about measuring circles to start. Then we're going to move forward into some theorems and some rules that have to do with circles. So just before we get rolling, I want to talk about if we have a line that intersects a circle, how many possible intersection points can that line have with that circle? So if we draw the possibilities out, possibility 1 would be that it doesn't intersect at all. It has 0 intersections with that circle. Okay, possibility 2 would be that we intersect in one place. That would obviously just be a line that just touches the edge of the circle, but doesn't go through it. Possibility 3 would be that we intersect that circle in 2 spots. Is it possible to intersect in more than 2? If we are drawing a straight line, it is not possible to intersect in more than 2 places. 0, 1, or 2 are the options. Now, to expand a little bit, what if it was a circle intersecting the circle? Well, let's draw our possibilities for this. So possibility 1 would be 0 intersections. The circles don't touch. They are not intersecting each other at all. Possibility 2 would be that they intersect in one place. That would be 2 circles that just touch each other on the edge. Possibility 3 would be that those circles intersect in 2 places. Those would be kind of like a Venn diagram appearance. And there's one more. That's possibility 4. This would be a situation where the circles are the same. They are on top of each other. And in this situation, we have an infinite number of intersection points because they are touching at all places. So just kind of a basic overview thinking about how circles and lines could interact with one another. All right, so with that kind of in the back of our minds, we want to talk about the parts of a circle. This is just kind of an introduction to some terms and some references we'll make as we deal with circles moving forward in the next 3 weeks. So obviously, very basic, we have the center of a circle. It's a point. We could label it with a letter. In this case, I did P. That point is exactly in the center. It is equidistant from every single point on the perimeter or the circumference of our circle. Any line that goes from that P to the edge would be a radius, obviously. Any line that goes through that point P from edge to edge would be a diameter. Another term of vocabulary is a chord. A chord is a segment that connects any 2 points on a circle. So to give you a few examples here, line segment AC would be considered a chord. It connects 2 points that are on the perimeter of the circle. Line FB would be a chord. Also a diameter as it goes through our center, connecting 2 points on a circle. ED would also be a chord. You can get the idea kind of what a chord would look like. Essentially just connecting 2 points on a circle. So A, C, B, F, and D, E are all examples of chords. Another term we want to be aware of is what we call a central angle. A central angle is simply an angle where its vertex falls on the center of a circle. So in this situation, angle AOB would be a central angle. It's an angle where the vertex falls at our center point. Our next term is what we call an arc. An arc is simply part of the circumference. Usually it is made by an angle that we see, a central angle, or what we'll talk about later is an inscribed angle. We don't have to worry about that just yet. So in this situation that we just had on our last slide, an example of an arc would be arc AB. It's part of the circumference. If we use two letters and we put an arc over them, that's a way for us to show and notate an arc that's happening in our diagram. Many times I choose to use three letters for an arc, just so people know which one I'm talking about. Because if you think about this example, I have arc AB, but what's to say that I'm not talking about this arc AB, right? We don't know which direction necessarily that we are traveling around that circle. So what we might do is add another point outside of our arc that we're talking about. And let's say that I wanted to talk about the larger arc, the one I drew in purple. I could call that arc AXB, showing 3 points that I'm using so that the person who's interpreting my diagram would know that I'm talking about the arc that goes around the larger part of the circle instead of the smaller. The other way that we can avoid doing that third letter would be using the terms minor or major. Sorry, I skipped ahead here. So if we wanted to talk about minor arc AB, that would be the smaller arc. It is smaller than 180 degrees. Okay. The flip side of that, if we wanted to talk about major arc AB, that is an arc that is greater than 180 degrees. It's bigger than half the circle. So it is a major arc, and that way we would know we're talking about the larger one. So again, we have a few different ways that we can kind of differentiate between which arc we're talking about. We can use three letters. We can use minor or major, meaning the smaller or the larger. Or we can think about this in terms of just basically differentiating for our reader using those letters to say, hey, I'm talking about the smaller one. We can use specific measurements. We can use those third letters. All right. The one piece of arc that we haven't talked about yet is a semicircle. A semicircle is just an arc that takes up half the circle, which I think we're pretty well aware of from our previous work. So how do we find the measure of an arc? It's very simple. To find the measure of an arc, we simply measure the central angle that, what I like to call eats the arc, essentially thinking about it like a big giant mouth. This is different than the distance. So make sure that we're aware this is not talking about how far that arc is or the distance of that arc being measured. We're talking about the angle. So in this situation that we've used previously, if I know that the measure of angle AOB is 120 degrees, then the measure of arc AB is also 120 degrees. As that angle eats that arc, it means that their degree measurement is identical. That being said, we can also find the measure of arc AXB. If we think about a circle, knowing that is 360 degrees, we can deduce that arc AXB would be 240 degrees as it completes the remaining part of the circle. So total would be 360. Now we want to talk about the length of the arc, not just the measure in degrees, but actually what is the distance or what piece of the circumference is that arc. So when we think about this, we want to think about it in terms of how long is the arc as it relates to the entire circumference. So back to this diagram we've used a couple times now. If I know that AOB is 120 degrees, how could I figure out the length of arc AB? Well, I would need some other information first. So in this situation, just for the sake of the example, let's say that our circumference of our circle equals 20 inches. Okay, if I want to find the measure or the length of arc AB, I first need to think about what percentage or what fraction of my circle is angle AOB. Okay, so 120 out of 360 is exactly 1/3 of my circle. So it would stand to reason that this arc would be 1/3 of my circumference. So with that in mind, if I take 1/3 of 20, we end up with about 6 2/3, I believe. So arc AB would be 6 2/3 inches. And all I did to find that was set up a basic proportion. So 120 degrees out of a total of 360 is equal to arc AB, which I'm trying to find, out of a total of 20 inches with my total circumference. Cross multiply and divide to find AB is 6 2/3. So simple proportions here, just proportional algebra, realizing that the percentage of our total that angle includes will be equivalent to the percentage or the fraction of the total circumference. All right, so we're going to look at a few theorems now that have to deal with chords. The first theorem says this: two chords are congruent, meaning the same, if and only if. Remember, if we have the word if with two F's in it, that means if and only if. That's our way to kind of abbreviate. If and only if their corresponding arcs are also congruent. So what does that look like in an example? Well, let's say we have chord AB and chord CD. And I want to say that those chords are congruent. Well, one way to prove that would be to draw central angles that include them. And if we can prove or are given that those angles are equal, 70 degrees, 70 degrees, then we would know that those chords are congruent based on this theorem. Because we know that the arc CD would also be 70 degrees, and the arc AB would also be 70 degrees. And this theorem says two chords are congruent if their corresponding arcs are congruent. So based on this theorem, arc AB is congruent to CD, so chord AB is congruent to chord CD. So this will be a theorem that we can use as we're proving some things in our assignment this week. If the arcs are congruent, then the chords are congruent. All right, so this would be a good point to pause if you want to just take a little break, or go ahead and take a look at the first 2 pages of that assignment that's posted. Before we move on, this is kind of a separate section talking about what we call inscribed angles. So it's a good place to pause and do some work if you want to. Otherwise, you're welcome to just watch the whole thing and do all the assignment at the end as well. Totally up to you. All right, so moving forward with section 10.4, this is what we call an inscribed angle. Inscribed angles are kind of interesting. They're angles that their vertex is not in the center, their vertex is actually on the circle. So for example, angle ABC is what we call an inscribed angle. Notice that vertex is not at point O, like those central angles we just dealt with. The vertex of B is actually on the perimeter of our circle. So we have what we call our inscribed angle rule. The inscribed angle rule essentially says that an inscribed angle is equal to half of the arc that it eats. So for example, if I have an inscribed angle, ABC, and I have a central angle, AOC, it's important to see that these both have the same arc that they are eating, right? We've got this one and we've got this one, but they're eating the same arc on the outside of the circle. If I know that that angle AOC is 120 degrees, I also know that that arc is 120 degrees. And based on my inscribed angle rule, I would know that that inscribed angle would be 60 degrees because it is half of the arc that it's eating. So we're able to deduce, given 120 degrees for this angle, this arc would also be 120 degrees. And because this arc is eaten by angle ABC, we know that it's half, so this angle would be 60 degrees. Let's draw another inscribed angle. So you can see here, angle ADC is another inscribed angle, but it also is eating the exact same arc as our previous one. So even though it's in a completely different place on the circle, it still eats arc AC, meaning that its measure would still also be 60 degrees. Just for the fun of it, let's throw another one in there. You can see this is an even weirder one. Angle AEC, still an inscribed angle, as its vertex is on the perimeter, and it still eats arc AC. So angle AEC would also be 60 degrees. So you can see many, many different angles could present themselves that all equal 60 degrees, as long as they're eating the same arc. So thinking about those inscribed angles, like I said, they will always be the same. They'll always be congruent if they're eating the same arc. So just to kind of make this a little clearer, let's do some color coding here. So A, B, C eats the exact same arc as A, D, C eats the exact same arc as A, E, C. You can see that all of them have endpoints here and here, meaning they will all be congruent. So, for example, if I told you that the measure of AOD was 150 degrees, based on that information, we would know that the arc AD is also 150 degrees. And because it is eaten by angle ABD, if that's the angle we're looking for, we would know that that would be half of that, or 75 degrees. Now let's say that I told you that ABD is 15 degrees. Because it eats arc AD, we know that it would be half of that arc. So that tells us the arc is 30 degrees. We know based on our central angle rule that AOD, because it eats that arc, will be equal to that arc because it's a central angle. So we know that AOD would be 30 degrees. Now let's say that I didn't give you a number per se, but I told you that angle ABD was X degrees. Based on that knowledge, we know that the arc AD would be twice that and equal to that central angle of AOD, which we would just call 2x degrees in this situation. So here would just be a basic variable example, knowing that this arc has to be double its inscribed angle, so it has to be 2 times x. And when we know that about an inscribed angle, we know that the central angle will be the same as the arc, so 2x. One more here. This time we want to find the measure of angle ABD. And I'll tell you right off the bat that it's 90, but what I'd like to do is prove why. We know that anytime we have a line that is a diameter, it's taking up exactly half the circle, meaning that this arc would be 180 degrees, half of our circle. With that being said, we know that the inscribed angle has to be half of that, which makes it 90, which if you kind of look at this sideways, you can see that is a perfect right triangle. So if you have a diameter or your chord goes through the center, we know that the inscribed angle that eats that arc will be a perfect 90-degree angle. All right, so hopefully that made some sense. Here's what you're going to see on your assignment today. We're going to have 3 different sections. So on page 710, you're going to just see some very basic kind of beginner circle terminology, labeling parts, that kind of thing. I would at least choose 5 to 10 problems from that page. It'll go very, very quick. Then I'm going to have you jump ahead to page 718, and all these pages and answer keys will be posted, so you don't need to worry about finding a book. They'll be on the website like usual. On this page, you're going to see just a little bit more, kind of based on what we did at the halfway point there on the slides. Chords and central angles, eating arcs, finding arc measurements. Again, I would choose probably 5 to 10 problems from that section. And then lastly, you're going to see page 727. And this is the one that's going to include more about inscribed angles and how they relate to central angles. Again, I would try to choose 5 to 10 problems from each section. If you have time, choosing 10 problems from each of these pages would really benefit you. 5 will get you some good practice, but doing at least 10 from each page will give you a nice chunk of work that's going to really help you understand this. Again, which problems you do are totally up to you. Pick ones that are interesting. Don't just choose the first 5 problems in the chapter, as they're going to be really, really easy. But pick some challenges, do what looks interesting, and then obviously use the answer keys posted to check your work as you go. So if you have questions this week, drop me an email. I'm happy to do that for you. As you know, those of you who've emailed me in the past, I usually get back to you within 24 hours. It's pretty quick. Also, that retake for coordinate geometry will be posted. If you finish that up, drop me an email and I'll get that graded and sent back to you relatively quick as well. But otherwise, until next week, stay healthy. Let me know if you need any help and have a wonderful day. Bye-bye.